So begin by defining each of these two terms. So numerical differentiation. So numerical differentiation is simply the process of calculating the derivatives of a given function by means of a table of given values of that function. So if we have only a table for values of x and the values of f of x, and we are asked to carry out the integration of the differentiation of the function that produced such a table, then we use the method called numerical differentiation. And then the way we carry out numerical differentiation is the same way we carry out interpolation, in that there are methods based on equally spaced intervals for the values of x, and there's also methods based on the unequally spaced values of x. Come in. In class, yeah? Yes, yes. The application of second and higher order derivatives. Okay. So to carry out numerical differentiation or simply approximation, of the derivatives can be obtained numerically using the following two approaches. So one, methods based on finite differences for equally spaced values of x or values of the mesh points. Now, when we say equispaced data, we simply mean equally spaced values of the mesh points. So there are methods based on either Newton forward or Newton backward. Number 2, so that's what we have. So we have methods based on finite differences for equally spaced values of data measurements, or methods based on divided differences, or the Lagrange interpolation for non-uniform data. So we shall revisit. On numerical differentiation methods. Those some of the formulas will not be asked to derive them, but you'll be asked to apply them. And once you have the differentiation formula, the application will not be very hard, because the same way we are carrying out interpolation, the same way we were reading the forward and backward difference tables, is exactly the same way you are going to apply the values of the derivatives when you are approximating a derivative of a function by table form or numerical differentiation. So let's define the next term, numerical integration. Now, numerical integration is a process of evaluating a definite integral from a set of tabulated values of the integrand. So the process of evaluating a definite integral in the interval, so integral a from a to b of f of x dx for a set of tabulated values is called numerical integration. So there are different methods of carrying out numerical integration, some of which include so there's one that you know from your high school, the so-called trapezoidal rule. Number two is what we call Simpson's third rule, or mostly we call it Simpson's rule. And number three is what we call Simpson's 3/8 rule. We have what we call Rompag's integration. So we'll start or describe robustly the first three methods. The last method of integration, the Rompag's integration, will not be done in class, but will be set in the exam, which is simply a repeated application of the trapezoidal rule. So check out how it works after understanding the application of trapezoidal rule. So we state the formulas without proof, but you can always find the proofs in the handout and the previous video classes. Time doesn't allow us to do the proofs. So one, trapezoidal rule. So the goal is to evaluate this integral So that's our main interest. So what we do, we divide the interval AB into n sub-intervals, each of size or width h given by b minus a over n. The formula is I integral from a to b of f of x dx is h over 2 into f naught plus fn plus twice f1 f1 plus f2 plus f3 plus fn minus 1. Then we close the brackets. Please remember, we are still using the same notation. When I write f naught, I mean the value of the function at x naught, which can be written as y naught. When I write f1, I mean the value of f at x1, which some people can write y1. So note that this formula can as well be written in terms of y values, but the interpretation is the same. So instead of using fi's, you can use yi's. So divide the interval AB into n subintervals, each of which is h. So h is given by b minus a over n. So the fi values are simply the ordinates. And when I say ordinate, I mean if this is my arbitrary function, y equals to f of x, then this way I have my a, and this way I have b. So what you are doing is to call this a, we are calling it x naught, b, we are calling it xn, and so you divide this into n subintervals. So this will be xn minus 1, this is x1, this is x2, etc. And so these small strips are assumed to be trapezium in nature. So this height is what I'm calling f naught. This height is what I'm calling f1. This height is what I'm calling f2. This is fn minus 1. This is fn. So the fi values are what we call ordinates. So these are called ordinates. And two ordinates forms a strip. So this is a strip. So strip is formed by two ordinates. And remember, if you have n ordinates, then you have n minus 1 strips. If you have n plus 1 ordinates, then you have n strips. So this is the famous trapezoidal rule, not a very new rule. You already have interacted with it at high school level. So with that in mind, let's state the structure of the formula for the Simpson's third rule. 2, Simpson's third rule. Simpson's third rule states that if I want to work out the integral from a to b of f of x, then I have h over 3 into f naught plus fn plus 4 times f1 plus f3 plus f5. Can you predict the next ordinate value?
F7.
F7, followed by other several terms, plus the last one will be f n minus 1, correct. And then we have f2 plus f4 plus f6. What will be the next one? f from f8, then plus other several values. The last one should be f FEB n minus 2, and condition to apply this, n must be an even number. So other things remain the same. This h is obtained by b minus a divided by n. But this is very key. We ensure that you are splitting the interval AB into an equal number of subintervals. That the number n should be divisible by 2. So in simple terms, to apply Simpson's third rule, there's a factor h over 3, and then inside we have 3 terms, where the first term is a summation of end ordinates. Second term, we are taking 4 multiplied by all ordinates which have odd subscripts, and then the last term is twice the sum of all ordinates with even subscripts. And before you apply the rule, n must be chosen such that it is an even number. Three Simpson's 3/8 rule. So to carry out the integral from a to b of f of x dx, we'll have 3/8 times h into, you take the sum of the end ordinates plus 3 times f1 plus f2 plus f4 plus f5. Can you tell me the next value? Plus 2 into f3 plus f6. Then I close the bracket. Are you in a position to predict the next f value from f5? If this is how the third term square bracket will be. F7, so we are skipping f6. So f7 plus f8 plus f10, etc., all the way up to plus fn minus 1. And then this will be f9, f12, all the way plus fn minus 3. And we restrict, for you to apply this is a condition. N must be a multiple of 3. So that should be very clear before you have to apply any of these 2 Simpson's rules. And please note that Simpson's rule implies Simpson's third rule. So when a question is open, whether it's specifying a third or 3/8 rule, then by default, when you talk of Simpson's rule, you mean Simpson's third rule. If you want to make a reference to 3/8 rule, then you have to specify that that's what you're implying. But when the problem is open, Simpson's rule by default means Simpson's third rule. So small break. When you come back, or during this break, I want us to discuss this problem. Solve using a trapezoidal rule So this is the integral -1 to 1 dx over 1 plus x squared. So the first thing I want us to solve this question 1. Trapezoidal rule first using n equals to 4. Two, n equals to 6. And 3, n equals to 8. In each case, compute the error and percentage error. So that's what we do after break. So a short break and then we come back to do that.